Question number 2. When one mole of monoatomic gas, when 1 mole of monoatomic gas expands at constant pressure, comma, the ratio of the heat supplied that increases the internal energy of the gas and that is used in expansion is option A infinity, option B 0, option C 3/2, option D 2/3. See, from thermodynamics first law we can write dq equal to du plus pdv, where du is the internal energy, increase in internal energy, pdv is the work done, and dq is the amount of heat supplied. Now I can write this one as Cp dt for 1 mole, since it will be n Cp dt actually, but for 1 mole I can write n equal to 1 and it will be Cp dt. This one will be du. Now we are having 1 mole of an ideal gas, so we have the equation of state PV equal to RT. Then it is expanding under constant pressure. So keeping P constant, if I differentiate both sides, it will be P dV, that will be equal to R dt. So this P dV is the work done, dW, that can also be represented here as R dt. So just substitute this in for P dV in that equation. So you will get here R dt now this Cp is how much? 5/2 R 5/2 R dt minus of R dt equal to du. Then taking R dt common, you can write 5/2 minus 1, that is 3/2. So 3/2 R dt, that is equal to du. So we can write du divided by R dt. But what is R dt? dW, that is equal to 3/2. This is the ratio of internal energy to work done. Because the amount of heat supplied dq is partly divided into internal energy and partly in work done. So their ratio has to be calculated in the problem. Okay. Question number 14. A gas is compressed adiabatically. A gas is compressed adiabatically till its temperature is doubled. Compressed adiabatically till its temperature is doubled. The ratio of its final volume to initial volume will be ratio of its final volume to initial volume will be option A 1/2, option B more than 1/2, option C less than 1/2, option D between 1 and 2. The adiabatic process, then it shows that Tv to the power gamma minus 1 equal to T2 V2 to the power gamma minus 1. Okay. Since the volume is compressed, then ratio of final temperature to initial temperature. So final temperature T2, initial temperature T1. So T2 by T1 will be equal to V1 by V2 to the power gamma minus 1. In the question it is asked the ratio of the final volume to the initial volume. Okay, means V2 by V1, that has to be calculated. Okay, so V2 by V1 will be equal to T1 by T2 to the power 1 by gamma minus 1. Now temperature is doubled, means T2 is twice T1, so it will be 1/2 to the power 1 by gamma minus 1. This one 1 divided by 2 to the power 1 by gamma minus 1. Now let us check for monoatomic. If I consider monoatomic, then gamma equal to 5/3, and if you put here, then it is 5/3 minus 1 means 2/3. So 1/2/3 means 3/2. So 2 to the power 3/2. So 2 to the power 3/2 definitely greater than 2. So this ratio is less than half. If you consider diatomic, then gamma is 7 by 5. So it is coming 2 by 5. So 1 by 2 by 5, that is 5 by 2. Again 2 to the power 5 by 2 is definitely greater than 2. So it is less than half. So the answer is less than half. Whatever be the value of gamma, it will always be less than half. Because for it to be equal to half, gamma should be equal to 2, which is not possible. Okay. Question number 17. A monoatomic gas of pressure gas at a pressure P, a monoatomic gas at a pressure P having volume V expands isothermally to a volume 2V, and then adiabatically to a volume 16V, Find the final pressure of the gas. Which law is obeyed by gas in isothermal process? Isothermal means temperature is constant. So PV equal to nRT. So if temperature is constant, then entire right hand side is constant. So isothermal process obeys the law PV equal to constant, that is Boyle's law. So for two different states, I can write in isothermal process that P1 V1 equal to P2 V2. Okay, P1 V1 equal to P2 V2. So now from this, initially P1 is given P, V1 is given V. It expands to 2V. So V2 will be 2 times V. So from this I can write that P2 equal to P by 2. This is the first part, isothermal. Then it expands adiabatically. Adiabatic process obeys this law. Then I consider that from after this step the gas expand adiabatically. So P2 V2 to the power gamma will be equal to some P3 V3 to the power gamma. When the gas In isothermal process obeys PV equal to constant. In adiabatic process it obeys the law PV to the power gamma equal to constant. So for two states, one is 2, another is denoted by 3. I can write P2 V2 to the power gamma equal to P3 V3 to the power gamma. Now P2, that is, already we have calculated P by 2. V2 is 2V. So it can be written as P2 equal to P3 into V3 by V2 whole to the power gamma. V3 by V2 whole to the power gamma. I divide this V2 to the power gamma on this side. Okay, now V3 is 16V. So write P by 2 equal to P3. This is 16V. This is 2V to the power gamma. For monoatomic gas, gamma is 5 by 3. V cancels, 2, 16 means it is 8. Then calculate. P2 by P by 2 equal to P3 into this one means 2 to the power 4, 2 to the power 3. So 2 to the power 3 into 5 by 3. So 3 is cancelled. So P3 equal to P divided by P3 equal to P divided by 2 to the power 6. 2 to the power 5 multiplied here with another 2 to the power 6. 2 to the power 6 is 64. So the answer is P by 64. So first part expands isothermally, next part expands adiabatically. So up to 2V it expands isothermally, so we use Boyle's law. The next part the gas expands adiabatically, so we use PV to the power gamma equal to constant. Okay. Write down question number 32. 1 mole of an ideal diatomic gas undergoes a transition from A to B. 1 mole of an ideal diatomic gas undergoes a transition from A to B along a path AB. Along a path AB, the change in internal energy of the gas during the transition is four, 6, 2, 5. Pressure in kilopascal and this is volume in meter cube. Calculate, no option. See, du, this is equal to n CV dt. So from this we can write n, what is CV for diatomic gas? 5 by R by 2. And dt means difference of temperature, that is temperature at final temperature minus initial temperature, TB minus TA. So this will give you delta U. Okay, then I can write 5 by 2 into nR TB minus nR TA. From ideal gas equation, PV equal to nRT. So I can write it is equal to 5 by 2 into PB VB minus PA VA. PB VB PA VA, all coordinates are given. Calculate. PB is 2 kilopascal, PA is 5 kilopascal, PB and VB and PVA both are 4 meter cube and 6 meter cube. Question number 44. An ideal refrigerator has a freezer at a temperature of minus 13 degrees Celsius. The coefficient of performance of the engine is 5. The coefficient of performance of the engine is 5. The temperature of the air to which heat is rejected will be. Temperature of the air to which heat is rejected will be. Option A, 325 degrees Celsius. See, I see that many of you are only collecting the solutions of the problems. Only collecting the solutions of the problem. This solution, write it. This solution, write it. And we will prepare a very thick note. And study all those notes before the exam. But in the physics, that will not be a fruitful case. After collecting notes, then you have to read, then you have to build the concept, and then you have to solve the problems particularly. Otherwise, whatever be thick note you can prepare, it will not help. Because don't think that this type of question will come. Write an essay, whatever you learned in physics in your life. This type of question will not come. You have to solve numericals. Coefficient of performance of the refrigerator beta equal to T2 by T1 minus T2. Okay, where T2 is the temperature of the freezer, that is minus 13 degrees Celsius. Beta is given 5, you have to find out the value of T1. T2 is given, beta is given, you have to only find out T1. So put the value of T2 and put the value of beta and solve for T1. T2 is temperature of the freezer, beta is coefficient of performance. And during calculation, remember, you cannot put minus 13 degrees Celsius. You have to convert it into Kelvin. In the First, minus 13 degrees Celsius has to be converted into Kelvin. Substitute there, find T1. T1 will come out in Kelvin, and then again convert it into Celsius. So it will be 39 degree Celsius. Okay. If it is a quadratic, then how many roots? 2. So maximum power and number of roots are always equal. If it's a cubic equation, then number of roots is 3. Okay, I will give you one equation and tell me the number of roots. A and B are not equal. It is also given that A and B are not equal, such that you may not arrive, this situation will not arise that this is undefined, that is undefined. It is given that A not equal to B. Okay, is it a linear equation or quadratic? Linear, because maximum power of x will be 1. Okay, fine. Suppose I consider x equal to a and check whether the equation is satisfied or not. This is a minus a, so 0. So this term is 0. This is a minus b by a minus b. So equation is satisfying. So 1 equal to 1. So left side and right side satisfying. So x equal to a is a possible solution. Okay, let us check x equal to b. B minus a by b minus a, that is 1. B minus b 0. So this is 0. So 1 plus 0 1. 1 equal to 1. It is satisfying. So how many roots? It's a linear equation. How can 2 roots come? For a quadratic equation earlier you said that 2 roots will come. In a linear equation I show you that there are 2 roots. How is it possible? It is satisfying. So I can claim that these are roots. Linear equation must have 1 root, but here it shows that 2 values are satisfying. How is it possible? Quota factory dekhe ho? Chemistry, everything is exception. Exception ka bhi exception. When Quota Factory first the session released, all the chemistry teachers are angry on the physics teachers, because whatever the chemistry colleagues of us in the institute, we shared the link of that episode. That student asked, this is chemistry is subject to exception. See, if you try to solve this one, x will cancel from the equation. Check, x minus a by b minus a. Take minus common from the denominator, x minus b by b minus a equal to 1, and check what comes. B minus a, x minus a minus x plus b equal to 1. X cancel. B minus a by b minus a means 1 equal to 1, which is always true. That is an identity. Means if you simplify this one, any linear expression, linear equation is like this: ax plus b equal to. But if ax plus b equal to 0, this is the standard form of a linear equation, and this is a linear identity. Means if you reduce it, you can write it in this format: ax plus b, 0 plus x is equal to b. Means 0x plus 1, that is equal to 1. So whatever be the value of x I can put. I can put x equal to a, b, c, d, e, f, z, anything. 0 into that will be 0, and 1 is always equal to 1. This is called linear identity. Similarly, quadratic identity can be prepared. It looks like equation, but it's not an equation. Whatever value of x you will put, 1 equal to 1, you cannot change. So whenever there is a structure of an equation and it shows that maximum power is 1 but the possible roots are more than 1, immediately consider that this cannot be an equation, because in an equation maximum power and number of roots should be always equal. Identity is the only type of mathematical entity for which power may be 1 but solution may be more than that. Power may be 2 but solution maybe you will get 3 to 4 solution, but it's a quadratic equation. Whenever this type of situation arises, immediately think that in the calculation somehow the coefficient of x will become 0. All powers of x will be 0. So it is not an equation, it is an identity. Okay. So this type of situation when arises in physics, in dimensional analysis you have used this one. Left side and right side, all the dimensions you m to the power 1, there is m to the power x plus z. Then you immediately write 1 equal to x plus z. So when this dimensional comparison is done, we are using that both sides are identical, means we are considering their identity. Okay, so for a identity, don't think that power and the roots are equal. Power and the roots, maximum power of the variable and the roots, number of roots are equal only for equation, not for identity. There is a distinction between equations and identity. Identity can be satisfied for any number of values, but for equation, specific maximum power and the number of solution must match. Okay. 1 minus T2 by T1. T2 is the sink temperature and T1 is the source temperature. So you have to find out T1, that is the source temperature. It is given that in the first case efficiency is 1/6 equal to 1 minus T2 by T1. If you decrease this T2, then efficiency will increase. So new efficiency will be doubled, means it will be 2 by 6. 1 minus T2 minus 62 divided by T1. Then from this, eliminating T2, you have to find T1. Because it is given that sink temperature decreases by 62 degree Celsius. No one asked me this question, that how you put 62 degrees Celsius. You are not converting it to Kelvin. Why I am not converting it to Kelvin? If you convert it to Kelvin, then you will be wrong in this case. Because 62 degrees Celsius decrease in means 62 Kelvin decrease. Same. Particular temperature in a Celsius scale and Kelvin scale, they are different, but the difference of temperature in Celsius scale and Kelvin scale are equal because the fundamental intervals are of equal length in Celsius and Kelvin scale. So decrease in temperature by 62 degrees Celsius is equivalent to the decrease in temperature by 62 Kelvin. So that's why when you are taking difference, the difference will remain same, but the particular value of the temperature will be different. So whenever you will put the data for T1, T2, etc., then you have to put in Kelvin. But if there is a difference, then degree Celsius difference and the Kelvin difference both are Kelvin scale difference both are equal. Because if you have two temperatures, suppose one is T2, another is T1 in degree Celsius. Okay, then if you convert it to Kelvin, then it will be T2 capital, in this corresponding temperature will be T2 minus T1, but that should be T2 plus 273 minus T1 plus 273. As a result, it will be T2 minus T1. So difference will remain same in Kelvin and Celsius, but the particular value of the temperature will be different. Particular value of the temperature in Celsius scale, when it is converted to Kelvin, it should be plus 273. But when so after substituting T2, when you solve T1, it will come in Kelvin. Then you have to again convert it to Celsius to match the options. So what is coming? See, from this equation, it will be T2 by T1, that is equal to 1 minus 1 by 6, means 5 by, implies that T2 will be equal to 5 T1 by 6. T2 will be equal to 5 T1 by 6. Substitute it here. So it will be 1 by 3 equal to 1 minus T2 minus 62 by T1. So we can write this one as 1 by 3 minus 1 equal to 1 by 3 equal to, sorry, 1 minus, first term will be T2 by T1, next term will be plus 62 by T1, right? I divide each term by T1. So first term will be T2 by T1, next term will be minus minus, so it will be plus 62 by T1. Then 1/3 equal to 1 minus T2 by T1, I already have the value, that is 1 by 6. So no need to calculate that, I can directly substitute this value. That is 1 by 6 plus 62 by T1. So it is 1 by 3 minus 1 by 6 equal to 62 by T1. So this one will be 1 by 6. 1 by 3 minus 1 by 6, that will be 1 by 6 equal to 62 by T1. So T1 is 372 Kelvin, which is 99 degree Celsius. 99 degree Celsius. Option D. we have two relations to eliminate two variables. One is T1, another is T2. So from the first equation, we have to find out T2 in terms of T1 and substitute in the second equation to solve for T1. Okay. Question number 6. A Carnot engine whose sink is at 27 degrees Celsius, whose sink is at 27 degrees Celsius, has an efficiency 40%, has an efficiency 40%. By how much should the temperature of source be increased? By how much should the temperature of the source be increased so as to increase the efficiency by 50%, so as to increase its efficiency by 50% of original efficiency. The options: option A 275 Kelvin, option B 325 Kelvin, option C 250 Kelvin, option D 380 Kelvin. Efficiency eta equal to 1 minus T2 by T1. First, it obeys Kelvin Planck statement, because if it draws certain amount of heat from the sink, from the source, it must reject certain amount of heat to the sink to produce some useful work. Because if it will not deliver anything to the sink, then efficiency will be 100%, which is not possible by second law of thermodynamics. And remember, tomorrow in the first study session, read simple harmonic portion such that you can solve the problem, at least 50% of problem, when I will give the problems in the class. And if you are not reading the simple harmonic motion and the morning study session, I can check. I will give one problem and ask any one of you to put the board and solve.